session today. So we'll discuss with Rafael about securing post-quantum implementations against physical attacks. So let's just start by introducing yourselves. So I am Adrian Thillard. I'm a principal security analyst at PQShield. So I hold a PhD in cryptography, and I specialize in designing side channel and fault countermeasures and also performing them in a practical setting. So just in a few words, at PQShield, what we are trying to do is to design the latest state-of-the-art countermeasures that would prevent physical attacks on post-quantum cryptography. So we will define what we mean by that. So you can see here some examples of the things that we published on side channel analysis and also on design of such schemes. So the aim of the company is to deploy post-quantum cryptography to the world's technology supply chain. So we will secure implementation for hardware and for software. And yeah, we are a team of scattered all around the world with cryptographers, engineers, operators that will help making those algorithms resilient against the quantum threat. We help shape the NIST standards, and we hope to keep shaping them. So I'm very grateful for PQShield for having me. We've been for eShard, sorry, for having me. We've been collaborating each other for a few years now on many topics, and yeah, I'm very grateful for them to offer this opportunity to co-host this webinar. Rafael, maybe you want to say a few words.
Yeah, definitely. Hello, everyone. I am Dr. Rafael Rodriguez. I'm a hardware security analyst here at eShard. Just a quick word about my work here on this company. Well, my work revolves around attack analysis and countermeasure development for embedded post-quantum cryptography. So I'm really happy to be here and thrilled for today's session. Before we dive in, a quick word on our company, on eShard. We are a French cybersecurity firm which empowers chip makers and security labs to understand how real devices behave under physical attacks. Our flagship platform, ESDynamic, brings all benches, tools, and project and automation in one single place, in a way that you can do your entire attack workflow from data acquisition to exploitation and documentation without leaving the platform. Over the last few years, we've worked a bit on post-quantum research, and we put this knowledge straight into our platform, which is called ESDynamic. It ships reproducible test benches for lattice-based schemes like ML-KEM, ready-to-use leakage assessment scripts, and reference countermeasure libraries so teams can benchmark fixes as fine as they find flaws. For example, here you have some examples of our latest addition of content for the catch-check has function. So in short, our platform ESDynamic lets you move from theory to silicon-level evidence in hours, not weeks. And that's exactly the mindset we'll use in today's webinar. Let's get started.
Thanks, Rafael. Yeah, so we'll start with a very broad introduction on physical attacks and cryptographic implementations, and then Rafael will delve into more details in and evidence one attack on such a scheme. And then I will give some examples about how to prevent your implementation against the attack that Rafael will demonstrate. So let's start, of course, by a very broad context on cryptography. So cryptography is the study of secure communication. So it covers data encryption, digital signatures, message digest, a lot of primitives. And nowadays, it is ubiquitous. You have it basically everywhere when you pay something with your card or with your phone, when you go to your office and you need some access control, when you go on the internet and your communication is encrypted, when you boot any firmware on any device and you want to be sure that it's not malicious, you have to verify some kind of signature. When you pass a border, you name it, it's basically everywhere. And cryptography is actually a science that has been around for centuries, if not millennia. And the way that it was being considered in the literature for quite a while was what we now call the black box model. So the black box model is this idea that you want to protect your algorithm against an attacker that will get access to an input and an output, which sometimes you can see as a plain text and a ciphertext. And basically, you want to prevent your attacker to learn any secret from your algorithm, which we call the key, that will transform this input throughout this output, and maybe allow him to do the inverse operation. So this is the study of the algorithm by itself. Like if you have an AES, which is a standardized algorithm, and you just see what goes in, what goes out, and you try to get the secret from that. But now the issue with this approach, which is still makes sense, but is that algorithm, they do not run out of thin air, right? They have to be implemented. They have to run somewhere on some device. And in particular, they could run on your computer, right? So this leads to this idea of a white box model where you would consider attackers that make use of this simple observation that an algorithm has to run somewhere, and that maybe they can root your computer, right? So what happens if now you are running an algorithm and the computer is within the machine, right? It has access, they have access to everything. They have access to input and output, sure, but they also have access to any device, any register at any moment. Like they could run a debugger maybe and modify some things. So this is what literature has called the white box model, where you have a super powerful attacker that can modify and do whatever he wants at any time. So of course, this is an interesting model, and this is also a model that makes sense in a lot of settings, but sometimes it's a bit of an overstretch, a bit of an overkill to consider some kind of such an attacker. For example, if I go to my supermarket and I buy some fruits with my credit card, I'm pretty sure that I don't have a remote adversary running a debugger on my credit card at the moment. But still, even though there's no remote adversary on my credit card at the moment, and the white box might be a bit too strong of a consideration, my credit card still has some physical reality. And it will be a bit too optimistic for me to think of it as a black box issue. So that's why there's this idea of a gray box model, which is somewhere in the middle, where you consider attacker that will still get access to the input and the output, and they will get access to something else that we call a signal, which is just the idea that there is a physical reality that can be exploited. And this leads to the definition of what we call a side channel. So a side channel is just a source of information that you can obtain by measuring some physical phenomenon. So once again, this idea that the algorithm does not run on thin air. And from this observation of the physical phenomenon, maybe he can get some information about what is running inside the algorithm. So this is the input, the output, and the signal. The signal is the side channel. So as an example of side channel, you can think of basically any physical quantity you want. For example, the timing. So let's say you have, you see that your device takes a bit longer than average to compute something, then it probably means that it's computing something that is a bit longer than average. I forgot to mention that if you guys have any question, just write them down in the chat, and we'll answer that in the end. Sorry about that. So the timing, might be an information about what is going on in the chip, but the power consumption can also be something that gives information. Like your chip is taking a lot of power, it probably means that there are maybe big operations going on. And you name it, electromagnetic emanations, sound, temperature, even photonic emissions, everything that you could observe to leverage physical, the physical reality of your device, this can be used as a side channel. So how do you use that to perform a side channel attack? Rafael will go in a lot of details on a specific example, but I just want to give you a basic idea there. So the attacker will, on one hand, measure these physical quantities. So let's say the time. And on the other hand, they will look at what's inside the chip, they will look at the algorithm, and they will try to select values that are interesting, and they are interesting in the way that they depend on some secret, like a secret key. And once they found variables that are interesting, they will apply what we call a leakage model, which is simply a way to say, okay, how do this initial intermediate variables, how these variables impact the leakage that I'm trying to measure. So for example, if my value has a lot of bits, maybe it will take a bit longer to process, and then I will have a timing that will be longer. And what they will basically do is make hypotheses on these variables and see how this moves the physical quantities that they are supposed to measure. And they will compare this with what they are measuring. Okay, and at some point, for some secret hypothesis that they will choose, they will get a match. So this match will allow them to say, okay, this is the secret that is actually being manipulated. And this comparison, it can be more or less easy. This can be a simple observation. This can be statistics, as we will show you, but this can even be deep learning models, machine learning, you name it. So this is the basic idea of side channel attacks. So one side note is that they are not that expensive nowadays. It depends on your target, but on most targets, this is not that expensive. You need basic acquisition card. You need some probes maybe with EM if you are measuring EM, but if you are measuring something else like the timing, well, you basically need something to measure the execution time. And you need very basic computing process. So all in all, you can mount a basic side channel bench for maybe €1,000. So in the worst case time, for some unprotected device, it will take you minutes of hours of work in order to recover this secret. So let me now introduce what we mean when we talk about post-quantum cryptography. So first of all, we have to consider what's called the quantum computer. So the quantum computer is a very active field of research nowadays. And this is based on this idea that physicists are trying to exploit quantum physics in order to build devices that will allow humanity to get a computing power that will be order of magnitude bigger than what we are able to do today. So using a new physical basis in order to build a supercomputer in a way. And we know since the 90s that the day this quantum computer exists, we can run an algorithm that will break the problem that's called the discrete logarithm problem. And this discrete logarithm problem, this is the building block of our classical cryptography as we know it nowadays. This is the basic block of RSA and of elliptic curve cryptography. Which means that the day that the quantum computer is actually accessible, this is the quantum apocalypse, right? We break every crypto system that relies on this assumption. And sure enough, every other month you have a big announcement of a big company or big country or big state that says, hey, we make a progress towards this building of the quantum computer. So they are slowly getting there, but they are getting there. And of course, we don't want to wait the quantum apocalypse to happen to say, oh, we need to react. No. Researchers try to change gears and say, okay, you know what? If this discrete logarithm is broken by quantum computer, let's build other algorithms, cryptographic algorithms, that do not rely on this hard problem of the discrete logarithm, but that rely on other problems, lattice-based, hash-based, multivariate-based, code-based, you name it. And so a lot of researchers built new crypto algorithms that will not be broken by this quantum threat. So these are algorithms that will run on classical computers, right? You don't need a quantum computer to run this algorithm. And their strengths rely in the fact that they will not be susceptible to an attack with the aforementioned algorithm. And of course, state actors are also getting involved in that. They don't want to wait the quantum apocalypse to happen either. And they launched some standardization efforts. So the main one is probably the one from the US, where they asked to researchers of the world to come with their best shot at cryptographic, post-quantum cryptographic algorithm. So there were dozens of submissions to the NIST, and several years passed. Researchers tried to attack each other, and in the end, NIST chose 4 algorithms: Kyber, Dilithium, Falcon, and Sphinx Plus, which they standardized with a very fancy name: ML-KEM, ML-DSA, FNDSA, and SLF-DSA. They are still doing this standardization effort. They are dealing with another algorithm that's called HQC at the moment. And basically what they said is, okay, now in 10 years, if you guys don't have these algorithms in your device, if you have not migrated to post-quantum cryptography, you will not be able to do business basically with the US government or any administration, right? So this will be mandatory to support post-quantum algorithm. And of course, US is not the only country interested in that. Sure, there are lots of standardization processes happening in other countries, Korea, China, lots of them. And you also have recommendations from security agencies. So I've cited ANSSI, which is the French security agency, BSI, which is the German security agency. And they push their opinions on which algorithm they feel are better than the other, which parameters should be used, and to what purpose. And of course, companies and universities, they are also very interested in this field of research. So there were dedicated sessions in hardware security conferences like Chess on Cascade, also in flagship IRCR conferences like Crypto, Asia Crypt, Eurocrypt, to propose algorithms, propose implementations, and propose attacks. And this is where eShard and PQShield, we were particularly active. eShard proposed a lot of attacks on implementations of such algorithms. And on PQShield side, we proposed design, and we also proposed many countermeasures in order to protect these algorithms from physical attackers. There is a challenge for protecting PQC against SCA being side channel attacks. First of all, the algorithm, they are quite long. So I must say that it really feels like hardware security was not the main criterion in choosing this algorithm. It is totally possible to protect them, but it's not always very convenient to do. They are long, they are error prone in the way that you need to check a lot of lines. And they use a lot of primitives that were not really used in classical cryptography. So there are a lot of polynomial multiplications, for example. We will give a specific example on an algorithm called the entity that serves this purpose. There are hashing algorithms like SHA-3, which is rather novel too. And a lot of primitives like Gaussian and binomial sampling, rejection sampling, decoding and encoding. Could give a lot of examples that are quite novel. And there's also the presence of what we'll call public key operation in specific instances. And basically what this implies is that you have a huge increase of values that can be sensitive and that could help an attacker to reach this key recovery. So now I will pass the hand to Rafael, and he will explain to you how, first of all, ML-KEM, and then how you attack ML-KEM.
Thank you, Adrian. Um, just a little moment. Perfect. All right, so let's dive into ML-KEM and how it works. So you must know that ML-KEM is the first NIST key encapsulation standard. Well, it received this name very recently since it was originally proposed as CRYSTALS-Kyber. There are many research papers about its physical security in the literature. So if you want to get inside this topic, you may search it as CRYSTALS-Kyber, right? This algorithm, it securely encapsulates a shared key for encryption purposes. So instead of directly encrypting a message to send it through an insecure channel, we are encapsulating a key that will be used with a symmetrical encryption algorithm. This encapsulation mechanism is also based on a problem that is called model learning with errors. So model learning with errors is a variant of the original learning with errors problem, which I will explain it right away. So it's stated as follows. We have a pair of elements, A and T. A is a matrix of integers modulo q. It has size m times k. And T is going to be the result of the operation A times S, which is called the secret vector, plus error vector. So A is sampled uniformly at random, and the secret and the error are sampled following a small distribution that here we denote as chi. Given this setting, the problem is stated as follows. We have two versions. The first version is the search learning with error, which we are asked to find S given A and T. And the second version is the decisional learning with errors, in which we are asked to distinguish between a learning with error instance that would be well, the element T, and a random sample. This problem may be hard according to parameters. For example, in learning with errors is parameterized according to the sizes of the matrix M and K. However, its performance is quite inefficient in the basic scenario. So researchers have come with a better way of improving this performance by adding some structure to the matrices, and we can by using this structure we can represent them into polynomials. That here the security parameter will be given by the degree n. We know how since as you see in the picture we're doing multiplications. We know how to do polynomial multiplications in efficient ways. However, by modifying the degree n, we have to always change the, let's say, the structure of the algorithms that we're going to use. So a better way to also improve the performance is to add another layer over ring learning with errors, which would be model learning with errors. Here, our elements are vectors and matrices that contain polynomials. And its security is parameterized by the sizes of these matrices and vectors. So now let's talk about how simplified model learning with errors public key encryption system would work. Let's start with the key generation and the encryption. So the key generation would be exactly as we showed before. We generate a random matrix A, we generate our secret S and E, and our public key will be the couple A and T. And our secret key will be our vector of polynomials S. To encrypt the message, what we will do is that we're going to draw a vector R. Here, let's call it the randomizer. This vector R, we're going to multiply it with our both parts of the public key, A and T. And then we're going to add an error. So each of these parts is going to be a MLWE instance. But to the second part, we're going to add the message encoded as a polynomial, right? So we're going to have two parts of our ciphertext, vector called u and a polynomial called v. I see there's a question, a raised hand. I think it's better if we address the questions at the end, right, Adrian? But if you can also write them in the chat. If it's simple enough, maybe we can like answer it in the way. Thank you. So how do we decrypt this message from our ciphertext? So if we take a look at our part of the ciphertext v, we remember that it was the multiplication of r times t plus the error plus the message. And if we expand the expression of t, we get our original model learning with errors instance from that was generated in the key generation. This looks very similar as multiplying u times s, since, as you remember before, u was the multiplication of r times a plus an error. So we're going to have something that is very similar to this. What we have to recover the message is just subtract this u times s and have an efficient decoding algorithm that allow us to remove the error from the result. So that's how decryption is done. We take our part of the ciphertext v, we subtract it with u times s, we obtain our message plus an error, and then we decode to take away the error from this result. So now let's talk about how we can attack a modular learning with error publicly encryption system or a key encapsulation system in the case of ML-KEM. The tool that we're going to use is correlation power analysis. Let's dig in, talk a little bit of basics about this technique. So Adrian showed you before, to perform a side-channel attack, it's all about comparison. It's all about having physical quantities on one hand and a leakage model on the other hand and comparing them in some way. Correlation power analysis it's a technique that states which statistical model we're going to use to do the comparison and how we're going to obtain the leakage model. So let's go first of how we obtain a selection function that will be used to compare it with physical quantities. So let's do a simple example. In this simple example, we have a plaintext and a key, right? The plaintext and the key are added, and then they go through a substitution function, subbytes here we call it, to obtain a result. This result is what we're going to use as intermediate values that depends on a public value and our secret key that we're targeting. So first what we do is that we make a guess on this key. And then we obtain the result of our known plaintext with this guess, going through the subbytes, and we store it here in the first, let's say, entry of our matrix. Then we go through all of our plaintext until we exhaust all of the values. So we obtain one column. And then we change the guess. And then we do it all over again with all of our plaintext until we fill this matrix that has size n, or with which n would be the number of plaintext that we have, and the number of guesses that can be done for this key. In this specific example, we're considering that the key is 1 byte, and therefore there's 256 possible guesses. Also, we're going to do this for every single part of the secret key. In this case, we had 16 bytes, and this is what's called a divide and conquer approach, since we're going to focus on each individual part of the secret key at a time, which allows to perform this attack in a quite efficient way without considering the whole key. These intermediate values are going to be fed into a leakage model, which is what we're going to compare with our physical quantities. What can be used as a leakage model? For example, we can use the number of ones that is set on each of the bit representations of the intermediate variable, sorry, which is what we call the Hamming weight. Or we can consider the transition between a previous state and a current state in terms of its bits representation, and this is what we call the Hamming distance. Then the other part that we need in order to complete our puzzle of how do we perform this comparison is our statistical technique to compare the physical world and our leakage model. And in the paper by Brier, Clavier, Olivier of 2004, which is called Correlation Power Analysis with a Leakage Model, they proposed the linear correlation distinguisher. Here we outline linear dependencies between our physical quantities and our leakage model. It is today's attack reference, and it's based on the Pearson's correlation factor. So how do we calculate this? We have calculate the covariance between our physical quantities and our leakage model of each of the columns, and then we divide them by the multiplication of the variances between the model and our physical quantities. This looks a bit complicated, but let's do a practical example of how this would work. So remember, we have our matrix of n times the number of n plaintext and the number of guesses that we can do for each of the parts of the key, and we have a matrix also of measurements that has I points for each of the traces and n traces. So we're going to calculate the correlation factor between our this column from our intermediate values that is fed to a leakage model, and each of the points of all of the traces. We're going to do this for all of the points, and we obtain what's called a correlation trace. So that has also size I, which would be the number of points. We continue doing it for each of the columns. Eventually, we will try with the correct column that guesses correctly the secret key. And our hope is that we're going to obtain a correlation peak that will be distinguishable from the others. We do this until we exhaust all of the guesses. So if we overlap our correlation curves, if everything goes well, it looks something like this with a correct candidate that that goes over the other correlation traces. So traces. And if all the assumptions that we did on the leakage model, on the number of traces that we needed, on the moment where the algorithm is being executed are correct, then we're going to see a convergence curve like this, in which if we augment the number of traces, we're going to see that our correct candidate will surpass the correlation value of all the incorrect ones. But this may also not be correct. This may also fail. This is not, let's say, an exact science or a magical tool that works always. But why does it fail? Well, sometimes the signal does not leak the expected information that we are thinking it will be. For example, there could be too much noise on the side channel acquisition, or that we haven't captured enough traces for the attack. If you're doing this correlation analysis through electromagnetic radiation, then it's possible that we are not positioning the probe in the correct part of our target. It may also be that we're doing the wrong assumption in the model. In the selection function, for example, the algorithm is not executing what we think it is executing. Or in the leakage model, it may happen that simply we have considered that it leaks at some way, but actually it leaks at the other way. It may also happen that everything that we all the assumptions that we did on the device are correct, but we are not targeting the correct operation in the time frame. Another possible source of failure is the misalignment of traces. It may happen that we're trying to obtain the traces at a certain pattern, and our pattern detection technique is not exactly correct and is unstable. And finally, another source of failure, which is more induced, is the presence of countermeasures. These countermeasures may be hardware-based. For example, the addition of noise to an oscillator in the board, or software-based by modifying the implementation and changing the way how intermediate variables are obtained, which is what Adrian will show you next. Now, let's talk about how we apply this technique to ML-KEM. So first of all, for our simulation, for our attack campaign, we have obtained these traces with a tool developed at eShard, which is called ES-Firmware. ES-Firmware is a register value-based trace simulation tool in which we target individual registers of our microcontroller. For example, we can focus on, let's say, on the program counter or a subset of the registers instead of capturing the activity of all of the device. We generate traces by using the value model or the Hamming-Weight model. For this simulation campaign, we simulated traces from the PQM4 project, which targets ARM Cortex-M4 microcontrollers. Here we feed random input ciphertext, and we add some Gaussian noise to the traces to make the attack more difficult. So let's talk about which selection function we will use to attack ML-KEM. So remember, we have always to find a function that depends on a secret key and something that we know, in this case, the ciphertext. In line 5 of the internal decryption scheme of ML-KEM/Kyber, we have the multiplication between the secret key S and the part of our ciphertext U. Well, as I mentioned before, the elements in ML-KEM are always polynomials. And the technique that we use to accelerate polynomial multiplication in this algorithm, it's what's called the number-directed transform, or the So the idea is that first we take every element, we have a polynomial, we transform it into the entity domain. In the entity domain, multiplication is it's less complex. It's linear. We point-wise multiply all of the elements of what we obtain at the entity domain, and then the result we invert it in order to obtain our answer, right? Our output. However, it must be noted that in Kyber, because of the choice of parameters, entity is incomplete. That means that we're not point-wise multiplying exactly every coefficient that we obtain in the entity domain. We have to do it in pairs. So we take pairs of coefficients from the ciphertext, a pair of coefficients of the secret key, and then we obtain a pair of results. This is the code that performs this pair point-wise multiplication. Just to note that we perform multiplications and then we perform the reduction with the Montgomery reduction algorithm. In the first part, we obtain the first coefficient, and in the second part, we obtain the second one. Then we packed the results in a single register since the values are in 12 bits. And we store 2 coefficients at a time in a single memory address. So it's always in couples. Every time we load something from memory, we load a couple. Every time we store something in memory, we store a couple. So how do you approach this attack? There are some considerations that we have to take into account. For example, there are multiple leakage points, multiple ways of performing this CPA, multiple multiplications that are performed. Which operation do we target? Well, in general, the store multiplications, they leak very well in microcontrollers, like for example, the STM32. But as I showed you before, the store operation involves two coefficients that depend on two coefficients themselves. So that means that we have to guess two coefficients at a time. This makes that the key hypothesis space is Q squared. And Q being 3,329, it makes a key hypothesis space of around 11 million guesses. So it's quite big. How do we manage this? Well, we may do an exhaustive search if we have enough computing power and enough patience. There are some works in state of the art that perform it like this. Another way of doing this is first doing a preliminary CPA attack in which we are attacking a multiplication that is stored in a register. This will not leak as well as the store operation, but may give us, let's say, a reduced hypothesis set that we can use to perform the attack. Another way to, let's say, increase our chances of success, it could be of using zero value ciphertext that may isolate leakage dependencies. For example, we can set one of the coefficients of the ciphertext to 0, and like this, every result will depend on only one of the coefficients of the secret key. So what we're going to do in this CPA attack is the second approach. We're going to target a single multiplication between two coefficients, one coefficient from the ciphertext and one coefficient from the secret key. There are two ways of doing this. We can attack directly the multiplication or the reduction. In this case, we're going to use the reduction since it removes some issues with shifts that have the same Hamming weight. And then when we have a reduced hypothesis set, we're going to use them to combine it with to target both the even and odd secret coefficients for the full multiplication. But here we're going to reduce, instead of Q squared, we're going to hopefully have something that is easier to calculate. So let's see how it works in our ES Dynamic platform. I can't seem to put this in full screen. I'm sorry. Just wait a second. Yeah, it's perfect. Hopefully you can see it. Yep. Perfect. So how do we do this in practice? So first, this is our, sorry, I am sorry, this little technical problem. We first, well, to know what we have in ES Dynamic is it's a Python environment in which we added libraries that make easier such analysis under control of benches. So first, we're going to import some of the libraries that will help us perform the attack. ESTraces is a library that allows us to manipulate trace object. Scared is an open source library that we developed at eShard to perform such an analysis. And then internal ES Dynamic libraries that, let's say, facilitate the visualization of the attack. We're going to import our dataset, which is stored in an ETS format. Our dataset, we have 10,000 traces, but we're not going to use them all, you will see. And some metadata, like the secret key and the ciphertext. Let's inspect our traces. So we're going to inspect 5 of them with our insight tool. We can see that everything seems nicely aligned. Here we can also like do some zoom to check the values and check that everything looks nice and correct in order to perform the attack. Now we'll define some functions and parameters. For instance, for the purpose of this demo, we are only going to target 32 couples instead of the full 128 couples of ML-KEM. This is only for for reducing the computation time and keep everything on schedule. We're going to define our reduction algorithms uh, with exactly what the word is doing, which is the Montgomery reduction. And then for the first part of the attack, as I mentioned before, we're going to target the multiplication between one coefficient of the secret key and the ciphertext. Be noted that in the board the values are signed, and we can do a little sign trick in order to reduce also the number of a hypothesis, since a multiplication with let's say comparing a multiplication with a positive value and a negative value, the result will roughly have, let's say, the inverse Hamming weight. So, for instance, if we do the correlation analysis and the correlation is negative, we can consider that the value is actually the guess is actually negative, and if it's positive, well, it's positive. So that's why we only take the positive part of the hypothesis. We define our selection function, which with our scared library. The selection function will be the reduction of the multiplication of the secret key and the ciphertext. And then we perform the first attack, which only involves one ciphertext, so one coefficient. We use 200 traces only. We define our selection function, then our leakage model, which would be the Hamming weight, our distinguisher, which is the linear correlation distinguisher, and a discriminator that helps us to distinguish which candidate is actually the correct one. We're just going to take the maximum absolute value of each of the correlation traces. We run it. Just wait a little second. And as you can see, for the word number 0, we have a negative correlation. So that means that our hypothesis was actually negative. And for the word number 1, we have a positive one. So we leave it like this. If we see the report of our attack, we can see that we found the expected correlation value for all of our words that we're targeting. So normally what we would do is that we would keep the guesses that correlate the most in the first attack. For facility, as we found the correct, let's say, coefficient for all of our words, we just keep that word. And then we use this reduced hypothesis set to perform the full attack, in which we attack the full multiplication that combines the couples. We define our entity multiplication, as I showed in the slides before. And then selection function that we take our new hypothesis set with the index of the couple that we are attacking. Then we're going to define a function to be able to parallelize this attack. Which is one of the advantages of the divide and conquer approach, that we can actually parallelize these attacks. Here, for the other coefficient, we are not going to not consider the negative part. We have to consider it, because if we, let's say, ignore the sign of both coefficients, we may obtain an incorrect result. So that's why we take it complete. We and this is the attack of how we do it here is going to be exactly the same. We take an attack object, we take our traces again, our 200 traces, our new selection function. We define above our module, our linear correlation distinguisher, and a discriminant. Also, to know that if the correlation is negative, we're going to invert the sign of what we obtain. We define our function, and then we're going to parallelize it with 5 cores. So you will see that with this attack will go real quick, just around 8 seconds. So we can see that our guesses were correctly ranked. It's always in the rank 0. We can like run a little function to check that everything was correctly guessed. And that's it. That's how we could attack and obtain the correlation. The secret coefficients from ML-KEM. Now Adrian will show you how to actually defend yourself from this type of attacks. We'll go back here and a little second. Oh, that's perfect.
That should be fine.
It's fine, yeah.
Thank you. Yeah, so we'll just go through several ways to protect these entity operations. Of course, there are a lot of possible countermeasures. I will just, for the sake of time, will just present 2 of them. One from the family of what we call hiding, and one from the family of what we call masking. So the first one, it's from the family of hiding. And it just starts from the observation that Rafael touched on, which is that the attack will only work if you look at the correct time sample, right? If you look at the wrong time sample, the attack does not work. And what this implies is that it will only work if every time sample that you are looking at for every curve is relating to the same value, that is the value that you are actually willing to target. So the first question that comes to mind is what will happen if you randomly shift those traces around? Then you can see that, of course, most of the time you won't get this correct value, and hopefully your attack will not work. So that's what we call jitter. And this is just this idea of artificially introducing random desynchronization in order to thwart the attack, right? So this gives rise to misaligned traces, and then the clean way for the attacker, if we follow what we just said, would be for each trace to guess where the sensitive variable is being manipulated, which is totally prohibitive. So let's try it. I took the code that Rafael showed, and I just added a small block that is basically a loop that does nothing, but that does nothing a random number of times, right? It gets some randomness from the outside world, and then it just decreases some counter from this randomness until this counter is 0. So this just creates like a little do nothing loop before the actual operation appears. And sure enough, I gave this code to Rafael. Rafael tried to attack with 200 traces, and as you can see, there's nothing there. There's no nice peak going on. The attack fails. But so good. This means that we actually achieved something. But the thing is that Rafael went a bit stubborn, and he took a lot more traces, and with actually 250 times more traces, he managed to get some interesting results. So sure, you see, these are not the peaks that Rafael showed just before, because they are not quite clear-cut, but you can still see what we would call still peaks, like you have values that stand out of each other, which means that the attack actually works just with more traces. So why is that? So this is just easy to understand once you think about it. Some of the points that Rafael targets are actually correct, right? Some of them are not, because we shifted the traces, but for sometimes it works. And if you add a lot of traces, then for a lot of traces you will have correct points. Sure, you will have a lot of noise added, but the signal will still be there. And statistics are very good to getting rid of signals, right? So that's why the attack works. He just needs to add more traces, but the information is still there. Another way he could have tackled this problem is by doing what we call a pre-processing. So if you take a step back and you look at the traces, so this is what Rafael obtained with the jitter traces, which is basically a mess. But if you look at it, you can see peaks. And these peaks, they relate to overconsumption, so multiplications probably happening. And if you take your time and if you detect this peak with a bit of signal processes, process, sorry, you can manage to realign those traces, right? And once you realign those traces, you can manage to get your attack in 200 traces. So the bottom line on this hiding and on this jitter is that it will increase the difficulty of the attack, but it will not thwart it. So I'm not saying that it's useless. It is not. It is actually quite useful to increase the difficulty of the attack. You can see it as some kind of obfuscation. You know, you manage to slow the attacker, and then he has to spend more time. So he either spend a bit more time on acquisition, like a linear factor of traces, or he has to run some pre-processing, some signal analysis, but he can achieve recovery this way. Now, the other family would be masking. And this is just a continuation of our thinking. Like I just said, the information was still there, and that was the problem. So if you want statistics to fail, what we want is the leakage to be statistically independent of the value that is being targeted, right? So if you consider your value, that is the sensitive value S, then you want to add some randomness to it in order to make it totally independent from S. That's what we call a sharing, an arithmetic sharing. In this case, you take S and you share it into two parts, into two shares that are S plus R on one hand and R on the other hand. And of course, R is totally independent from S. This is a random. And S plus R is also independent from S. And now your goal is to compute what you wanted to compute, but prevent S of being manipulated alone. Instead, you want S plus R to be manipulated and R to be manipulated. So, of course, you would have to do that for every primitive of your algorithm. That's why we said that it's a bit tricky to do. You will have to do it on the decompress, on the bytecode, on the byte decode, maybe sometimes, depending on what goes in. But on this case, we want to protect the entity. So what would happen there? You would take the value that we are wanting to compute. You take the formula, which is inverse entity of S times entity U. And there you see S is sensitive. So you take S and you replace it by S plus R minus R, right? So R minus R is 0. So I just mathematically changed nothing. And then I used properties of the functions that I'm looking at. So the transposition is linear. So this allows me to split, right? I have S plus R and R. And then the entity is also linear, so I can split it again. And in the end, I managed to get twice the operation I had in the beginning. So I have the exact same operation, but twice, and running on different variables. Instead of running it on S, I have been running it once on S plus R and another time on R. So of course, this means that I punch my performance. I'm twice as long, but hopefully I'm secure against an attacker. So is it secure though? Once again, we did that, get that code to Rafael, and he tried to attack with 50K traces, and the attack fails. So we are quite happy. And it fails because the information required to attack is actually split in different parts of the traces. So with this simple CPA approach that Rafael showed, the attack is actually probably infeasible. Even if we have taken millions of traces, would have changed nothing. You won't be able to attack this way. If you want to attack this way, if you want to attack, he needs to perform what we call a higher order attack. So a higher order attack is just this idea that the information is still somewhere in the trace, but it's split in several areas. So if an attacker wants to get the information back, he needs to take the one area where S plus R is manipulated, the other area where R is manipulated, and then to combine somehow those points in order to recover the information on the couple, S plus R and R. And this couple actually gets information on S. So that's the way he could attack. However, this would be exponentially costly for him, right? Let's suppose he would have need 1,000 traces that would take 1 hour to acquire. Then instead of 1,000, he will now need the square of that. So that would be 1 million, okay? And instead of 1 hour, that would be more than a month. So as a designer, as a developer, we pay the price by multiplying the time that it takes to do the operation. But as an attacker, we made him put a square on his attack. And sure enough, if I think that as an attacker this is not secure enough, well, I can still combine that with some jittering or some hiding countermeasure, but I can also, if I want, add another chair. I add a third chair, and now instead of S plus R, I have S plus R plus R prime, and I can still split it. Instead of taking me twice as long, it will take me 3 times as long. And now if he only looks at the 2 shares, then he only gets information of something that still does not depend on the sensitive value. So you will tell me, yeah, but then he can look at the 3 shares, or the 3 areas. And sure, he can. But now, instead of requiring 1 million traces, a square, he will need a cube. So he will need 1 billion. So instead of 1 month, it will be 80 years, right? So there will be always this cat and mouse game between the developer and the attacker. But the thing is that the developer will pay a linear price, while the attacker will pay an exponential price. So by carefully computing your risk assessment and by carefully choosing your trade-off, you can put the border where you want as a developer. So let's conclude in a few words this presentation. So of course, post-quantum algorithm, crypto algorithm, they are very vulnerable to SCA attacks, and they need to be protected. So there are countermeasures that exist and that can be implemented to protect them. However, you need to carefully compute a trade-off between the performance that you want to get and the security that you want to ensure. So in this talk, we went very in surface, and we showed you how to protect one operation, which is the entity. But as we mentioned in the beginning, there are several primitives. There are actually a lot of primitives that need to be protected, and each of them, they come with their own challenges. They are more or less complex. Some of them are non-linear. Entity was quite good to protect because I could split easily, but that's not often the case. So SHA-3, sampling, you name it, a lot of parts that are hard to protect, but we know how to protect them. And they all come with their different trade-offs. So of course, there will always be a cat and mouse game between the attackers and the defenders. But as I mentioned, as a defender, you can increase your security arbitrarily if you're willing to pay the cost. Of course, this is tricky to do, but the expertise exists. That's what we do. We try to develop countermeasures that are strong enough and that are as efficient as possible in order to get the trade-off the best way for the developer. So that concludes our talk. So, well, thank you everyone. Thank you, Guillaume.
Thank you, bye.